Dear students, today we will discuss the response of equilibria to the when pressure is changed and temperature is changed, and then we will discuss on Vant equation. First points we will discuss is response of equilibria to change in pressure or volume. Okay, suppose we have an example that is N2 plus 3H2, there is ammonia production, that is Haber ammonia process. Okay, this equation is the octane. In this equation, ammonia has the 1 mole and hydrogen has 3 mole, and the product obtained is the 2 moles. Okay, from reactant you will obtain the product, and a different mole of product is obtained. If same mole of reactant gives the same mole of product, that reaction not affected by the change in pressure. But those reaction which is having the different number of moles is for reactant and the different number of moles for the product. Okay, first point, we have clear that in this reaction total number of moles is changed. That is, total number of moles of reactant and product are different. Such reaction is only affected by change in pressure or the volume. Already we have discussed in previous video, but some part is remain, therefore we have discussed in this lecture. The total number of moles of reactant and the products are different, therefore total number of moles is changed in this reaction. If first way, if you decrease the pressure, okay, for this reaction if you decrease the pressure, and decrease pressure means there is increase in volume. If if you increase the pressure, there is decrease in volume is there. Okay, for this reaction equilibrium we can given as, okay, Kc, okay, reaction equilibrium, or Q you can given as the product, okay, NH3 raised to its stoichiometric coefficient 2 upon the concentration of the product, okay, product of the concentration of the reactant raised to its appropriate stoichiometric power. Therefore N2 raised to its 1 is the no need to write the 1, then H2 raised to 3. If you increase the pressure, okay, in this case you have increases the pressure, you found that your numerator, that quantity is numerator, that quantity is increased due to its exponent is 3. Okay, more 2 and 3 is the more exponent, therefore the product of this is the increase. Therefore this divided quantity is increased, therefore your Q value is going to decrease. Q value going to decrease. And if your Q value is decreased, and in this case less than 1 or less than the K equilibrium constant, then we know that for this case reaction is proceed to this side. Okay, therefore we can say that when pressure is increased or decreased in volume, your reaction proceed to that side where less number of moles is there. Okay, in this case 3 and 1, 4 mole is for reactant, For product 2 moles is there. Therefore, where is less moles? For the product 2, it means there is a less moles than the reactant. Therefore, your reaction, when you pressure is increased or decreased, that is ultimately it means the decrease in volume, then your reaction is proceed towards the product side, that is having the less number of moles. Okay, we can say when pressure is increased such where total number of moles is changed. Okay, the 4 and 2, that change in moles, that is total number of moles of reactant and total number of moles of product are different. If you increases the pressure, that reaction, your equilibrium is shifted to that side where less number of moles is there. This is decided by observing this equation. By reading this question Q, we can predict where is the reaction is proceed. If suppose reaction if like that, if it is having the 2 moles and if you having the product having the 4 moles, it is having 2 moles, then you increase the pressure, your reaction equilibrium will be shifted to the left hand side. Okay, where less number of moles is there, your reaction equilibrium is shifted on that side, whether it is shifted to the product side or whether it is shifted to the your reactor side. It depends upon how many number of mole is the present. Less number of moles is there, whether it is product or the reactant, your equilibrium is shifted on that side where less number of moles is there. In this case, less number of mole is associated with the product, therefore your reaction equilibrium will be shifted to the right hand side. Okay, and if your pressure is decreases, the explanation we have given for the pressure is increased, the same explanation oppositely, okay, vice versa explanation is for when you decreases the pressure. When you decreases the pressure, your equilibrium will be shifted, the more number of moles is there, therefore your equilibrium is shifted from left hand side to the right hand side. Therefore Q is increases when your pressure is decreases and volume is increases, and your equilibrium shift where more number of moles is the present. Okay, this is all about the response of the equilibria to the when you change the pressure or the volume, when gases, all the reactant and the products are gases. Second one is the what is the response of equilibria to temperature. Okay, if suppose you have from X to Y, you obtain the product, and suppose reaction is exothermic. Reaction is exothermic means the heat is evolved. Remember that heat is evolved, and therefore heat is evolved means the heat is evolved means from this side to heat is evolved. Therefore, in this case, heat is reduced from X to the when you convert X to the Y, heat is get less. Okay, in this is reduced or the less. If second you have the endothermic reaction. Endothermic reaction means it get the heat. Okay, it absorb the heat. Therefore, heat is evolved from Y to X. Therefore, in this case, heat is removed. Okay, from heat is removed from Y to X. In this case, heat is removed from X to Y. Okay, therefore, in exothermic reaction, heat in this enthalpy, okay, heat content associated Y is the H2 and heat content associated is the H1. In exothermic reaction, heat is exhaust. Okay, therefore heat is exhaust from Y. Therefore, this is the H2 has the less value and H1 has the higher value. Okay, therefore H2 minus H1 less minus you are higher. Therefore, delta H is equal to, you found that delta H is equal to less minus higher value, that negative. For your exothermic reaction, delta H is the negative. For your, this is the endothermic reaction. In endothermic reaction, heat is gained, therefore it is H2 has the higher heat than the H1, therefore H2 minus H1 is equal to delta H is equal to positive. Remember, for endothermic reaction, delta H change in enthalpy is the positive. Enthalpy is the heat content. Heat is absorbed in the product in the endothermic reaction, and therefore its heat content is increased, therefore it's higher H2 than the is reactant, therefore H2 minus H1, higher value minus lower value is positive. In this case, less value minus higher value is the negative. Therefore in this case, when you heat, okay, you add the heat to both reaction, that therefore temperature is increased. Okay, ultimately it increases. You add the heat, then when you add the heat, the equilibrium is shifted where heat is removed. Where heat is removed. When you add the heat to this exothermic reaction, means the temperature is increased, heat is removed from X. Therefore, for the exothermic reaction, equilibrium is shifted to the left-handed side. To left-hand side where heat is removed. And in endothermic reaction, when you heat is supplied and temperature is increased, then in endothermic reaction, your equilibrium will be shifted from X to the Y, where heat is removed from Y. Then in these cases, heat is shifted. Okay, remember that when reaction is exothermic or whether reaction is endothermic, your equilibrium is shifted where the heat is removed from that system. That is, it is having the higher enthalpy. It is having the higher, and your equilibrium shifted to the higher enthalpy content. Therefore, equilibrium shifted to the H2 in this, and equilibrium shifted to the left hand side in an exothermic reaction. This is all about the responses of the equilibria for the when temperature is changed. Then we will study the Vant-Hoff equation, which give the idea about endothermic and the exothermic reaction. Okay, therefore we have for Vant-Hoff reaction, Vant-Hoff, okay, that for Vant-Hoff formula, we will find out the Vant-Hoff formula. Okay, we have the relation that is G is equal to G naught. Okay, delta G is equal to G naught plus RT Ln PB upon PA. That relation we have studied. And delta G naught means it is a difference of, okay, difference of gives free energy of product and reactant when both is present at a standard state. Product from the standard reactant, you will obtain the product that is called a gives free energy at the standard state. But delta G is the change in free energy you can find out at any stage of reaction from the reactant to the product. But delta G0 is the for standard state. It is difference between the gives free energy when there is a difference, that is when the from standard reactant you obtain the standard product. 1 molar reactant you obtain the 1 molar product and at a standard state. But delta G is a change in free energy at any stage of reaction you can measure, and it's not at the standard state. Okay, delta G0 is the standard state. We will obtain this from the literature. Okay, therefore at equilibrium, okay, we have studied at equilibrium delta G change in gives free energy will be 0. Okay, at the equilibrium, at the start if reaction is proceeded at the start to the product, at the start its G value is the more, okay, higher G value, and you know that higher G value is there, higher gives function, higher gives energy is there, is try to remove the energy and try to obtain the stable state. If the any system has a higher heat content, it means it try to obtain the stable state by losing the energy. Okay, it loses energy, and at a particular it loses energy there, that is delta G something. At the particular point, the final that G2 minus G1 is equal to delta G0. That point is equilibrium there. Okay, when equilibrium occurs, when delta G becomes 0, then equilibrium is obtained. Therefore, delta G is the 0. Then by putting the 0 value, delta G naught plus RT ln PB upon PA. Okay, then G naught, delta G naught is equal to, that is, will transfer this side, minus RT ln PB upon PA. Okay, we have studied that this P change, okay, that this is obtained for the reaction A gives the B product. Okay, therefore this means the partial pressure of product, B is the product, partial pressure of product B and partial pressure of reactant A. This is a term we have studied. This is term is a Kp, or okay, that is equilibrium at the pressure in the terms of the partial pressure, and this may be equal to Q at equilibrium. Kp is equal to Q, that is reaction quotient at the equilibrium. This term we have studied, that is the Kp term. Okay, therefore we will write delta G naught is equal to minus RT ln Kp. Okay, by replacing this value, this is equal to Kp. Therefore this will be transferred to the delta D naught G naught, okay, G naught upon RT, okay, minus, so this will be transfer is equal to ln Kp. Okay, this delta naught G naught is equal to, we know that delta G naught is equal to delta H naught minus T delta S naught. Okay, this equation we have studied, and when we give the negative sign, you also give the negative sign this side, therefore the positive sign will be negative and the negative sign will be positive, and when you divide by RT, then each term divided by RT, and if you divide RT, TT is the cancel and R is there. Okay, therefore delta G naught RT is equal to minus delta H naught upon RT plus delta S naught upon R. Okay, this new equation is obtained. Okay, then we will take this ln Kp is equal to minus delta H naught RT plus delta H naught, that is R. Correct, TT we have cancelled, R is there, delta S naught, R negative sign for delta H naught. Okay, therefore for different two temperatures we will obtain this equation. Okay, therefore T1 for T2 for different two temperature there is no difference in no change in delta H and delta S is there. We assume that there is no change in delta H and delta S. R is the constant. These both terms are the only T is changed and Kp value will be changed if you change the T. First, ln Kp1 is equal to minus delta H naught RT1 plus delta S naught R. This is the first equation, and second equation ln Kp2 is equal to minus delta H naught RT2 plus delta S naught upon R. Okay, this is two equation we have obtained, and that two equation we have obtained, then we will subtract equation 1 from 2. Okay, then we will subtract equation 1 from 2. Okay, this will we have written. Okay, then equation from 2 we subtract the equation 1. Therefore, ln Kp2 minus ln Kp1 is equal to minus delta H naught RT twice plus delta S0 upon R. Okay, then minus this term. Okay, minus this term, minus plus. Therefore, plus delta H naught upon RT1 minus. Okay, the minus plus and minus delta H0 naught, because we will subtract from this. Therefore, all the signs will be changed. Therefore, minus delta S naught upon R. Okay, this positive and this negative will be removed. Therefore, delta H naught upon RT. Okay, RT1. Okay, positive will take this side, and delta H naught RT2. Okay, positive will take that side. Okay, therefore is equal to delta H naught. Okay, common term we will remove R in bracket 1 upon T1 minus 1 upon T2. Okay, that now we will obtain in bracket 1 upon T1 minus 1 upon T2 ln Kp2 and ln Kp1. Okay, if A gives the product B at the temperature T1 and T2, if you increase the temperature T1, T2 and the T1, you will find that in this case your T2 is higher than the T1, and therefore T1 minus T2, or if you T2 or T1, okay, T1 minus T2 will be negative, and the negative means your temperature is increases. Therefore, in other words, when you increase temperature for the endothermic reaction, it will favors the forward reaction. This is all about Vant-Hoff equation. I hope you will get the Vant-Hoff equation. Thank you very much.